we're going to explore some fascinating everyday science questions. How can people people work barefoot on intensely hot coal without immediately getting burned? The answer is simple: coarser pores and full of air, so they have a relatively low heat capacity compared to our skin, and lower thermal conductivity. The surface of the core might be extremely hot, but the heat moves very slowly from the cold surface to our feet. Also, because the heat capacity is low, the total amount of energy they can transfer isn't that much. It only works because you make the contact time super short, so there isn't enough time for the heat energy to actually cause a burn. Have you ever seen a demonstration where someone briefly dips their hands into boiling hot oil? The reason behind this incredible feat is due to what is called the rainforest effect. What is the rainforest effect? The hands-on moisture creates a temporary steam globe that shields the skin from the intense heat for a very brief moment. The second the super hot temperature hits our hand, the moisture on our skin instantly boils and turns into steam. This layer of high pressure steam acts like a thin shield between our hands and the boiling oil. Since the vapor layer has super low thermal conductivity, it blocks the hot oil from making direct contact with our skin and seriously slow down the heat transfer. And remember, this whole thing only works for a split second. Let's look at common household item. Why can hand sanitizer be a fire hazard? The main ingredient in hand sanitizer, ethanol, is seriously flammable. Since most sanitizers are over 60% alcohol, their flash point is super low, around 20 degrees. That means if you mess with fire right after putting it on, before the alcohol dries, you could start a fire.
Good day, Dr. Wu. I'm Eugene, and now I'll be continuing onwards with question 4. And some of the magic tricks that I found which relate to the concepts shown in the videos are listed here. So the first one is known as the methane mamba, and it is a magic trick involving creating methane-filled soap bubbles. And what the magician does is that he will ask the participant to scoop up a handful of these bubbles from a basin and light them on fire. And what results from that is that a giant tower of flames erupts from their open palm, and yet their hand remains unburned and unharmed. This magic trick can actually be explained as the methane burns upwards rapidly due to convection, as after all, the hot air will be less dense than the cool air surrounding it. And at the same time, the water in the soap film and on the participant's palm absorb the heat as it evaporates, and as a result, it protects the skin from absorbing that heat and getting burned. And so, what we can say is that due to the high specific heat capacity of the water in the soap film, it is able to protect the participant's hand. Now, we're gonna watch a video demonstrating this magic trick in effect.
So what we want to do is to be able to show the protection of your hands. Your hands are going to be protected because of the water. So here's what I'm going to do. I happen to have some methane over here.
Well, of course.
So yes. So why wouldn't you have some methane? So this is methane over here.
And we all know that methane's, well, a little flammable.
Yeah, well, just a little.
Big
right?
beach ball
so,
now.
So here is the methane, and here is my container, and I'm going to put some soap down in the container like this. So that'll be perfect. Got it?
Got it.
So now here's what we're going to do is we're going to push the methane down inside here so we just get methane bubbles. All right?
okay.
So here, I'm just going to squeeze.
Okay.
Oh, is that great?
Oh, those are excellent.
So Mark, what I'm going to ask you to do is this: get your hands wet, make sure they're wet, because we're going to breathe. Or we're going to allow the methane bubbles to start to rise.
Okay, all right.
That kind of fun? No, not yet. It's not big enough. All right, so there you go. And now that's a pretty good shot. So just kind of hold those. All right. So that's methane right there.
Methane
and so
bubbles
now
are warmer
your
than
hands
the other
a
bubbles
little
are.
bit. Stay there. Don't move. Isn't that great?
Gee whiz.
Isn't that fun?
Look at that.
Ta-da.
Look,
Now,
Tom.
your
1,
skin
2,
would
3,
have
4.
burned off if you didn't have the water. But here's what happens. Water is this great conductor of heat, and it steals the heat away from that flame. And so as that water starts to evaporate on your hands, it's a cooling sensation on your hands.
Yeah, they weren't even warm.
We know
was
that with
amazing.
fires, that fire department will try to get something wet or put some of that polyfoam that's on there to try to make sure that.
We're gonna do it again.
Well, we're going to do it many times. Are you kidding? All right, so here we go. This is just methane. So this is the favorite thing to. No, not yet. This is the favorite thing from a chemistry teacher. They love doing the no, a little bit more, a little bit more, a little bit more. All right, that's a good one right there. All right, ready?
Well, as
So
my
you're
hand's being set on
you're
fire, we'll do a
okay.
bigger pile
You're
of bubbles
fine.
then.
You're fine. See, isn't that just ta-da? You're perfectly fine
But
because
you can
the
feel
water.
the heat. You can
Do
feel
you
the
think
heat
so,
coming
Sparky?
off of it.
Yes, you can feel the heat. Smokey the Bear, you
that's
can.
fun.
Isn't that great?
Another trick I found, which is actually quite similar in principle to the methane mamba, is known as the unburning money trick, where instead of making bubbles, the magician borrows a paper bill and soaks it in a liquid solution and then sets it on fire. And although the bill is engulfed in a large flame, when the fire dies down, the money actually remains intact and dry. This is because the liquid isn't any random liquid, but rather it is a specific mixture of 50% alcohol and 50% water. And when the bill is lit, the alcohol, which has a lower flash point, burns. However, at the same time, the water absorbs the thermal energy which is generated by the alcohol. And similar to the previous trick, due to the high specific heat capacity of the water, it absorbs the energy without without transferring much of it to the bill, and in which case it prevents the temperature of both the water and the bill from rising significantly. And this is further exasperated by the phase change as the water evaporates due to the latent heat of vaporization, thus preventing the bill from igniting. Let's watch this video demonstrating the unburning money trick in action.
Bearded Science Guy here, and today I'm going to show you an experiment where it looks like we're burning money. To begin with, pour equal parts 91% isopropyl alcohol and water in a heat-resistant container. Make sure to stir the solution so that both liquids are mixed together well. Dip your money in the solution until it is completely covered in the mixture. If any part of the bill is dry, it will actually burn when you light it. Light the money and watch it burn. What you'll notice is that even though flames are coming off, the money itself is not burning. The heat energy being given off by the combustion of the isopropyl alcohol is being absorbed by the water present. If you don't use enough water, the money will burn after the water evaporates. One last piece of safety advice. The drips from the isopropyl alcohol will likely catch your table on fire, so don't perform this experiment around anything flammable or over top of a table that isn't flame resistant.
And now we move on to the final question, question 5, which is also a reflection on the task as a whole. And through these tasks, I would say that me and my teammates have learned these two main things. The first thing is on heat transfer as well as the properties of different materials. The different materials have different specific heat capacities as well as thermal conductivities, and that can affect how the heat is transferred between them. For example, in the very first video, which shows the fire walking stunt, we know that it is only possible because the coals themselves are poor conductors of heat, showing that they have low thermal conductivity, and that short contact time of the person walking on the coals helps to limit the total heat transfer into the high specific heat capacity of the human body. And what this means is that Number one, even when the person has a short time, not much heat is able to transfer over to the body. And at the same time, due to the high specific heat capacity of the human body, a lot of heat needs to be absorbed for it to increase significantly in temperature. And as such, the person does not feel the heat of the coals. And the second one, or second reflection, is on the usage of physics for education and entertainment. Now, as a science education student, I have to comment on this, of course. The magic tricks in this video actually really captured my attention, and I believe that it is actually something which can be used for students in teaching them about physics. Because by showing them and explaining to them the physics concepts behind a seemingly impossible or very impressive magic trick, it can actually spark curiosity in these students towards physics concepts, in this case specifically about heat transfer. And I feel like videos like this or demonstrations like this are potential gateways to increasing scientific interest in school students. I hope that you had a lot of fun watching this video. I hope that it has been informative as well as entertaining to you. Thank you for watching.
Okay, Assalamualaikum and hi everyone. My name is Taufik bin Muhammad Aziz, and today I will share to you guys from what I learned from the 6 videos in the module 4 about heat transfer in cooking, and also I will give reflect on how cooking device works using thermophysics. So the next slide is so here what I learned from the video is from the videos I learned that heat transfer is the key to how fast and how evenly food cooks. So here there is 3 main heat transfer methods we use in cooking. The first one is conduction, the second one convection, and the third one is radiation. Heat transfer is actually controlled by physics. Different foods heat differently depending on their thermal properties. So we have for the 3 method cooking. So the first one is conduction. Conduction happens when heat moves through direct contact. For example, pan frying, searing, or grilling. The heat moves from the pan to the surface of the food. This is why the outside cooks fast, but the inside takes longer to cook. So the next one is convection. Convection is when heat is transferred through moving fluids like water or air. This happens in boiling, steaming, or baking in an oven. Hot fluid or hot air circulates and creates more even heating, so the food cooks more evenly. So the last one is radiation. Radiation used in infrared heat. This happens in boiling or when using a blowtorch. The heat travels in waves and hits the food surface directly. So for the next slide is from the module 4. The videos also explain 2 important physics equations. The first one is Q, as we can see here, Q equal to mc delta T. And then the second one is L equal to root power of 4 dt. For the first one, Q mc delta T, this equation tells us how much heat is needed to raise the temperature of food. For example, beef heats slower because it has higher density and heat capacity. Tuna heats faster. And then for the second one is this equation predicts how fast the heat moves inside the food. If a food has high diffusivity, like fish, it enters quickly. If it has low diffusivity, like beef, it heats slowly. This is why large or dense foods needs longer cooking times, and why molten chocolate cake stays soft in the middle. The heat cannot reach the center fast enough. Okay, so here the diffusivity in different foods. There are 3 examples here. So you can see tuna with high diffusivity, beef with low diffusivity, and the molten chocolate cake with very low diffusivity. For the tuna, it moves fast, cooks quickly, and good for selling. And for the beef, it moves slowly, outside heat faster than inside. And for the molten chocolate cake, edges cook first, center stay molten. Heat cannot reach the time middle in short time. So for the next slide is cooking device reflection. So here, the chosen cooking device is I'm choosing the frying pan because frying pan mainly works using conduction. The metal pan heats up and transfer heat directly to the food surface. This makes it very good for searing things like beef or tuna. So, however, the inside of the food heats slowly, so we need to manage time and temperature properly. If we use a convection oven together, for the bonus one, if you use the convection oven together with pan searing, the circulating hot air helps cook the inside more evenly. So for the conclusion, overall, the videos help me understand that cooking is actually full of physics. Now I know why different foods cook at different speeds and why cooking methods matter. So far, I understand the heat transfer help us cook better and more consistently. Thank you for your guys listening me.